Hi Bobcats. In this video we'll look at some more subtle points about titrations. We're going to take a look at what the titration curve for the titration of a polyprotic acid looks like, as well as looking at how you would pick an indicator for a particular titration. So our objectives are to compare and contrast the titration curves of weak acids and bases and to select that appropriate indicator for a titration. When you're titrating a polyprotic acid, we make some assumptions about how the chemical reaction takes place. So let's say we're titrating something like well, let's just leave it general and call this acid H2A. So I'll have H2A reacting with hydroxide ion, and neutralization reactions we normally write as one-way arrows. So this would make water plus HA minus. And the general idea is that because of the values of Ka, we would expect that out of all of those molecules that are floating around in solution, every molecule is going to lose one proton first. And then after all of the molecules have lost one proton, we will see the second proton coming off. So after that first reaction happens, then HA minus can react with hydroxide ions to give us another molecule of water plus A minus. This is sometimes referred to as a stepwise reaction. So we kind of think of the titrations of diprotic acids is happening this way and creating a curve like you see in this diagram where there are two distinct equivalence points marked A and B. This is actually really hard to see in practice. In order to truly see two distinct equivalence points, there has to be a very big difference in size between Ka1 and Ka2. So Ka1 would be the equilibrium constant for the loss of the first proton. Ka2 would be the equilibrium constant for the loss of the second proton. Most of the times these titration curves get kind of smeared out and there might be just kind of a little wiggle where the equivalence point should be. We do tend to think of these reactions as happening stepwise, but that stepwise process only happens if there's a really big separation between the sizes of the Ks. All right, one more point to look at here, and that is selecting an indicator. You will find that if you go and you look up the pHs at which various indicators change color, you will find that the indicators change color at all sorts of different pH ranges. And generally speaking, if you are doing a titration that will have an equivalence point of a given value, like say here where the equivalence point is 7, you're looking to use an indicator that changes within about 1 pH unit of your equivalence point. So typically for something like a strong acid, strong base titration, we'll use phenolphthalein. It changes at a pH that's just a little bit past 7. Having that color change be just a hair past your equivalence point, that means then that your endpoint and your equivalence point will not quite be the same. And it appears to be a really big difference if you look at the pH scale, which is the vertical axis. But if you look at the horizontal scale, which is the volume of base added, those two values for the volume at the equivalence point and the volume at the endpoint are so close to one another. It's a fraction of a drop typically. And so usually you're in really good shape if your equivalence point is within about 1 pH unit of where your indicator turns color. All right, so we looked at a little bit about the shape of a titration curve for a polyprotic acid, and we also looked at how to select an appropriate indicator for an acid-base titration.